Hello everyone, my name is Dr. B. Deivanayagame, Associate Professor, Department of Physiology from Sri Lakshmi Narayana Institute of Medical Sciences, and I am going to talk about glomerular filtration rate. So what is glomerular filtration rate? It is defined as volume of filtrate formed by all the nephrons per minute. A normal value is 125 ml per minute. That means around 7.5 liters per hour or 180 liters per day. So normally the plasma volume is about 3 liters. So 180 divided by 3, 60 times per day. That means the entire plasma is getting filtered 60 times per day. So more than 180 liter per day is filtered when that 178.5 liters per day is getting reabsorbed and 1.5 liters per day is getting excreted. That means 1.5 liters of urine is passed per day. Okay, so out of 180 liters. And dynamics of glomerular filtration. The forces determining a tissue fluid formation the same for GFR. That means the starting forces. One is the hydrostatic pressure gradient across the capillary wall, and next one is the osmotic pressure gradient across the capillary. So according to Starling forces, the rate of fluid exchange, that means filtration or absorption at any point along a capillary depends upon a balance between these two forces, that is the hydrostatic pressure as well as the osmotic pressure gradient. And the driving force for glomerular filtration is the net ultrafiltration force across the glomerular capillaries. So, GFR is the sum of hydrostatic and collard osmotic forces across the glomerular membrane, so which gives the filtration pressure and the glomerular capillary filtration coefficient. So, GFR, we can write that as Kf multiplied by net filtration pressure. So Kf, I told that glomerular capillary filtration coefficient. So GFR is equal to glomerular capillary filtration coefficient, and the net filtration pressure is PGC. In the bracket you can write PGC minus PBS, suppose bracket minus pi GSC minus pi BS. So what is Kf and PGC and PBS, and you can, so about that we'll talk. So I told this same only here the glomerulus. So I told that Kf permeability, Kf, I told that filtration coefficient, it depends on, one is the permeability of the capillaries, and next one is the size of the capillary bed. So this is the effective filtration surface area. So Kf, that is the filtration coefficient, is normally it is around 12.5 meter square per minute per millimeter of mercury. So next one is the net filtration pressure. So we have told that PGC minus PBS minus pi GC minus pi G by PS. So that what is PGC? PGC is glomerular capillary hydrostatic pressure. So what is the value? It is around 60 millimeter of mercury. And PBS or Bowman space hydrostatic pressure, it is around 18 millimeter of mercury. And next one is a pi GC or glomerular capillary oncotic pressure. That means that is around 32 millimeter of mercury. And next one is a pi BS, that is a Bowman space oncotic pressure. It is around 0 because the filtrate which is present in the Bowman space, it does not have any protein. So the value is 0. Okay. So we can put the formula, we can write that. So PGC we can write as hydrostatic pressure. Pi PBS we can write as Bowman space hydrostatic pressure, and then pi GC we can write as glomerular capillary oncotic pressure, and pi BS is the Bowman space oncotic pressure. So we have talked about that. Next, So we can write that net filtration pressure is the net outward force. So it is here only the outward force, it's not the inward force. So outwardly force, which is acting on glomerular filtration rate. That means net filtration pressure is the net outward force and is calculated as the difference between the outwardly, that means that is the PGC and 5BS, and inwardly PBS and 5GC. So GFR is equal to Kf multiplied by net filtration pressure. So GFR is equal to Kf PGC minus PBS minus pi GC minus pi BS, I told before. So we put the values there. I have showed that PGC values as well as the pi BS values. So when I write the values there, I told that filtration coefficient, it is around 12.5. So I have wrote that. So multiplied by 60 minus 18. 60, I told that it is a PGC, it is around, it is a glomerular capillary hydrostatic pressure, it is around 60. And PBS, it is the Bowman space hydrostatic pressure, it is 18, and minus 32 minus 0. So you got the value as 12.5 multiplied. So you got the value as 10. So multiply by 12.5, you got 125 ml per minute. That is the normal GFR. It is the GFR value. It is around 125 ml per minute. And next one is the factors affecting GFR. So what are the factors affecting it? The first one is a change in renal blood flow. Whenever the renal blood flow increases, GFR increases, and whenever it decreases, GFR decreases. So it is directly proportional. Next one is glomerular capillary hydrostatic pressure. So whenever the glomerular capillary hydrostatic pressure increases, the GFR increases. So here also it is directly proportional. And next one is change in capsular hydrostatic pressure. It is a Bowman's capsular hydrostatic pressure. So GFR is inversely proportional to the capsular hydrostatic pressure. So it is vice versa. That means whenever it increases, GFR increases, there is a glomerular capsular hydrostatic pressure increases, GFR decreases, and if it decreases, it is decreases. So it's why it is inversely proportional. And next one is the oncotic pressure. GFR is indirectly proportional to the colloid osmotic pressure. And next one is the constriction of afferent arteriole. Whenever there is a constriction of the afferent arteriole, GFR decreases, but it is also inversely. Afferent arteriole constriction causes decrease. Whenever the afferent arteriole is constricted, GFR decreases, whereas constriction of the afferent arteriole causes increase in the GFR. And next one is the permeability of the capillary membrane. Whenever the permeability of the capillary membrane increases, GFR increases, whereas when it is decreases, GFR decreases. And next one is the effective filtration surface area. When the effective filtration surface area increases, GFR increases. And if it is decreased, the GFR decreases. So it is also directly proportional. And next one is the size, shape, and electrical charge of the macromolecule. So the GFR also depends on size of the molecules, shape of the molecules, electrical charge of the molecules. So size increases, GFR decreases, size decreases, GFR increases. Shape also discussed. And next one is the sympathetic stimulation. Whenever there is a mild sympathetic stimulation, there is no change in the GFR. Whenever there is a strong stimulation of the sympathetic nervous system, there will be decrease in the GFR. And systemic arterial pressure also influences the GFR. So these are all the factors affecting the GFR. So next one is the filtration fraction. What is filtration fraction? It is the fraction of renal plasma which is getting filtered per minute. The fraction of the renal plasma which is getting filtered per minute. That is the ratio of glomerular filtration rate to the renal plasma. So normally filtration fraction is equal to GFR, that is ml per minute, divided by renal plasma in ml per minute. So 125 ml is a GFR per minute divided by 700 ml per minute is the renal plasma flow per ml per minute. So you are getting the value of around 0.16 to 0.20. That is 16 to 25 or 20% of the renal plasma flow is getting filtered. And next one is the regulation of GFR. So how it is regulated? how the GFR is getting regulated. One is the auto-regulatory mechanism. It is divided into one is the myogenic mechanism, Duplo glomerular mechanism. Another also is the glomerular balance. And next one is the hormonal mechanism, and next is the neural mechanism. So one by one we will discuss about that. So what is auto-regulatory mechanism? The regulatory mechanisms affect the renal blood flow and glomerular filtration rate by changing the arterial resistance. So before discussing the mechanism, it is worthwhile to understand the relationship between the selective changes in resistance of afferent and efferent arteriole and the GFR. Whenever I told before itself the factors which affect the GFR, I told. Whenever there is constriction of the afferent arteriole, so you can see this is the afferent arteriole, this is the glomerulus, this is the efferent arteriole. Whenever there is a constriction here in the afferent arteriole, the GFR is decreasing as well as the renal blood flow also will be decreased. Whenever there is a dilatation of the afferent arteriole, there will be increase in the GFR as well as increase in the renal flow. Whereas afferent arteriole is normal, whereas there is a constriction of the efferent arteriole, there will be an increase in GFR but decrease in the renal blood flow. And next one is whenever there is dilatation of the efferent arteriole, GFR decreases, whereas the renal blood flow will be increased. So this is a relationship. So now we are going to talk about the myogenic theory. So what is myogenic theory? It is the intrinsic property of the arteriolar smooth muscle to contract when it is stretched. So intrinsic property of the arteriolar smooth muscles. What happens whenever it contracts, whenever it is getting stretched, it contracts. So when more blood passes through the afferent arteriole to the glomerulus, the wall of afferent arteriole is getting stretched. Hence, it contracts, reducing the blood flow. So what happens? It is contracting and reducing the blood flow. The intrinsic response can be blocked by drugs like papaverine, procaine, as well as cyanide. And next one is the tubulo-glomerular feedback. So what is that? Whenever there is increase in the renal arterial pressure, there will be increase in the GFR. This in turn causes increase in the sodium chloride concentration in the tubular fluid. So what is tubular glomerular? I'm talking about that. So increase in the renal arterial blood pressure. So this in turn causes increase in the GFR, in turn increases sodium chloride concentration in the tubular fluid. This is sensed by the macula densa cells. So in feedback effect, there will be a constriction of the afferent arteriole. So now what happened? There will be a decrease in the afferent arteriole. So this negative feedback. So the same like that. Whenever there is decrease in renal arterial pressure, there will be a decrease in the GFR. So this in turn causes a decrease in the sodium chloride concentration in the tubular fluid, sensed by the macula densa cell, feedback effect, dilatation of the afferent arteriole, and thereby increase the GFR. So vice versa. So this is called as tubulo-glomerular feedback. And next one is the glomerular balance. The intrinsic property of tubes to increase reabsorption rate in response to increased tubular load is so in turn causes increase in whenever there is increase in the high GFR. So when there is increase in the high GFR, there will be increase in the ontotic pressure of plasma in the efferent arteriole and peritubular capillaries. Solute and water reabsorption from the renal tubule. So this in turn causes increased GFR, causes reabsorption of solute and water from the proximal tubule. So the percentage of solute reabsorption in proximal tubule is held constant. So contraction is caused by endothelins, hormones. Next one is a hormonal one. Endothelins, angiotensin 2, vasopressin, norepinephrine, platelet activating factor, platelet-derived growth factors, thromboxane A2, PGF2, leukotrienes C4 and D4, and histamine. They all causes contraction, where relaxation is caused by ENP, dopamine, PGE2, as well as cyclic AMP. So hormonal influence on the GFR. I told before that first one auto-regulatory mechanism. Next one is the hormonal influence on the GFR. So hormones which causing vasoconstriction are norepinephrine. So decrease the extracellular fluid volume, and this in turn decreases the GFR, and thereby decrease both it is causing the decrease in the GFR as well as renal blood flow. And next one is angiotensin 2. This also decrease the GFR as well as affect on renal blood flow. So this also decrease the GFR as well as renal blood flow. And next one is the endothelin. They both also acting as a decrease the GFR. This also the causes vasoconstriction and they are causing decrease in the GFR. And vasodilators like prostaglandin, there will be no changes. Prostaglandin, there is no change in GFR. Whereas nitric oxide, bradykinin, atrial natriuretic peptide, glucocorticoid, dopamine, so glucocorticoid. So everything causes increase in the GFR by causing vasodilatation. Whereas dopamine as well as histamine, there is no change. So other all factors along have that. Whenever there is vasodilatation, there will be increase in the renal blood flow. And next one is the neural regulation. Both afferent and efferent arteriole are innervated by the sympathetic nervous system. So we know that the afferent arteriole as well as efferent arteriole are supplied by the sympathetic nerves. The sympathetic activity in the renal nerve is less when the blood volume is normal. The sympathetic activity in renal nerve is less when the blood volume is normal. When the blood volume decreases, increased sympathetic activity and increased catecholamine causes renal vasoconstriction, that in turn decrease renal blood flow as well as GFR. So whenever there is blood volume is decreased, sympathetic activity also increase, causing increased catecholamine release, causing vasoconstriction, and this in turn decreases further decrease in the renal blood flow as well as GFR. So how it is measured? GFR is measured by the renal clearance test. So what is renal clearance? Renal clearance is defined as the volume of plasma that is cleared of a substance in 1 minute by excretion of the substance in the urine. So unit of renal clearance is C. And the formula for that is C is equal to UV by P. So before that, you have to know the principles governing the renal clearance. You consider that substance A, it is getting filtered through the glomerular. So what happened here? So it is getting filtered and is fully excreted in the urine. So example for the substance which is getting filtered only. So it is not getting reabsorbed or secreted is inulin. So this substance we are going to use. Next one is it is getting filtered and partially reabsorbed. For example, the substance B example is urea. So it is filtered from the glomerulus to the glomerulus, from the glomerulus, and then next one is going to the tubules. So it is getting partially reabsorbed. So example for that is urea. So this substance also we are using for measuring the GFR. And next one is the filtration as well as completely reabsorption. Complete reabsorption. Example for that is sodium, glucose, amino acids, chloride, and bicarbonate. So this substance we are not using for measurement of GFR. So here what happened? They fully filtered and fully reabsorbed. So we can't use this substance for measuring the GFR. And some substances, what happened? It is getting filtered as well as secreted. Example, it is PAH or diuresis as well as creatinine. So we are using these three things. The substance A, substance B, substance D. In substance A, so we are using it is fully filtered. It is not reabsorbed, neither reabsorbed, neither either reabsorbed or secreted, which is the substance A. Example is inulin. We are using for the measurement of GFR. Next, I told that it is filtered as well as partially reabsorbed. Example is urea. This substance we are using for measuring the GFR. Whereas we are not using is fully filtered and completely reabsorbed. We are not using. Whereas substance which is getting filtered as well as secreted, it is creatinine as well as PAH as well as diuresis. So these three substances we are using for measurement of GFR. The first one we are going to take the inulin clearance test. So inulin is a difructopolysaccharide. It does not exist naturally in the body. So it is not naturally occurring. It is found in the roots of the certain plants. So what is the characteristics of the substance? I told that it is freely filtered by the glomeruli and neither reabsorbed nor secreted by the tubules. So the substance A we are using here for measurement of renal clearance. And it is biologically inert and non-toxic. So we should not use a toxic substance. Okay. So here we are using non-toxic substance. It is a inulin. It is neither metabolized nor stored in the kidney. So it is not metabolized and it is not stored in the kidney. Its concentration can be easily measured. So that's why we are using this inulin. It is fully filtered and completely freely filtered, as well as it is not reabsorbed as well as the secreted, and it is not non-toxic as well as it is not metabolized. So we are using inulin for the clearance test. Okay. So in inulin clearance test, so we are using, it is not produced for the naturally occurring in the body also. Okay. So how to measure the method? A single bolus dose of inulin is injected, followed by continuous intravenous infusion at a rate which compensate for its units loss. So now what happened? Concentration of inulin is equal to UV by P. I told that. So UV inulin V, that is the urine flow rate, divided by plasma concentration. So C inulin is the concentration of inulin, whereas U inulin, it is the urine flow rate, V, it is the plasma volume, and the V, volume of urine, multiplied by the P inulin. So we put the values there. Urine concentration of inulin, it is 35 milligram, and urine flow rate, it is 0.9. Plasma concentration, it is the 0.25. So you got the value as GFR is equal to 35 multiplied by 0.9 divided by 0.25. So you get the value as 126 ml per minute. So what is the clinical application of inulin clearance? In addition to its use as a measure of GFR, it is also used as an indicator of plasma clearance mechanism. A comparison of the clearance of a given substance with the clearance. So we are comparing of the clearance. So when you have given substance, you are comparing with the inulin. It provides the information about the renal transport process used to remove the substances from the plasma. So you have to compare. You can compare a substance X along with the inulin, and thereby we can get the information about the renal transport process. So which is used to remove the substance from the plasma. So when Cx, that is the unknown substance, equals C inulin. So that is when clearance ratio is 1. So when the clearance ratio is 1, the substance, unknown substance, as well as the C inulin will be equal. The ratio of clearance of substance and clearance of urine such a substance is characteristic similar to the inulin. Example, so it is having the similarity. So when you tell that it is having the ratio is 1, so it is same like inulin. Example is mannitol, sorbitol, ferric cyanide, vitamin B12, sucrose. When Cx is less than inulin, C inulin, it is the clearance of unknown substance is less than the inulin. When the clearance is less than 1, such substance with clearance below that of inulin are filtered and reabsorbed. So what happened? If it is 1, so it is filtered as well as reabsorbed. The example of substance clearance ratio less than 1 is glucose, xylose, as well as fructose. And when Cx, that is the clearance of unknown substance, is greater than C inulin, when clearance ratio is more than 1, substances with clearance above that of inulin it is getting filtered as well as secreted. That is, excretion is by the filtration and secretion. Example is PAH. So we can compare the clearance of inulin as well as the unknown substance, and thereby what happened? We can get the transport of this, how it is transported. And next one is a creatinine clearance test. Creatinine clearance test is less accurate than the inulin. It is not that much accurate in comparison to the inulin clearance. In clinical practice, creatinine clearance is preferred because of continuous IV infusion required in inulin clearance. What happened? It is cumbersome to give continuously the IV infusion of inulin. So instead, creatinine clearance is more. Somewhat but the accurate test is inulin clearance, but it is comfortable is clinically, which is useful is clinically we can do is creatinine clearance. So creatinine is an endogenous substance. It is a byproduct of muscle metabolism. It is filtered by glomeruli and marginally secreted by the tubules. And method, creatinine content of 24 urine collection and the plasma concentration in sample collected at midpoint of urine collection period. The formula C, that is the clearance of creatinine, is equal to U creatinine V divided by plasma concentration of creatinine. So U creatinine is the concentration of creatinine, V is the flow rate, and B is the plasma concentration of creatinine. The normal values 80 to 110 ml per minute in adult and declines with age in healthy individuals. And next one is a urea clearance test. Urea is an end product of protein metabolism. After being filtered by the glomeruli, that is partially reabsorbed by the renal tubules. Hence, urea clearance is less than the GFR. Further, it is influenced by the protein content of the diet. Hence, urea is not sensitive as creatinine clearance. Method. At the beginning of the test, the patient is asked to completely empty the bladder by voiding the urine. The exact time is recorded. Exactly after 1 hour, patient is asked to void again and quantity of urine is exactly measured. The levels of urea are estimated in the urine and the blood sample collected at the midpoint of the test. So now urea clearance drastically changes when volume of urine is less than 2 ml per minute. So it changes when it is less than 2 ml per minute. Two empirical indices have been used for urea clearance. Maximal urea clearance is calculated from the usual formula. This is applicable when the urine output is more than 2 ml per minute. So maximum urea clearance is calculated from the usual formula. That is the maximum urea clearance is UV by T. Whereas standard urea clearance is used when the volume of urine is less than 2 ml per minute. That is C, clearance of urea. That is standard urea clearance test. Yes, you can put that. So you have to write that UV by the square root of U into V by. Okay, so we got the values. Normal values, maximum urea clearance 75 ml per minute, whereas standard urea clearance is 554 ml per minute. Calculation, a proportion of urea reabsorbed by renal tubules remains relatively constant about 40% of the filtered, and urea clearance multiplied by 1.2 is a rough clinical estimation of GFR. Thank you for getting this opportunity. Thank you all.